Welcome to your podcast for Lesson 37, Coefficient of Friction and Inclines. After watching the podcast, you should be able to solve for the correct coefficient of friction depending on the motion or the non-motion of an object on an inclined plane. So if you take a look at the warm-up activity, we have a wood block on an inclined plane and it's just starting to slide when that plane is raised to make an angle of 30 degrees. So because it's just starting to slide, that tells us it's at that point where it's at its maximum static friction. Okay, so we're going to be solving for mu s here. And you'll notice the only number we have is a 30-degree angle. Okay, so let's go to another screen and draw this. Okay, so here is what your free body diagram should look like. The only other thing that we need to add in is that we know that this is at a 30-degree angle, and so we know that that angle is equal to this angle right here between FWY and FW. Okay. Now we don't have an actual mass given to us for this particular block, but we do know that FW equals mg. Some important things to keep in mind. Because we know that this is at the point where it just starts to move, that tells me that my FWX is going to be equal and opposite to the force of friction. I also know that for all of these problems, whether it is sitting on a flat surface that's completely horizontal or whether it's on an angle, we know that normal force has to be equal and opposite to some component of weight. So because this is on an incline, I know that that normal force is going to be equal to the y component of weight because that's what it's going in the opposite direction of. So FWY is equal to Fn. Now again, I don't have numbers that I can actually plug in for the mass of this block, but we can write some equations for FWX and FWY, which will ultimately help us solve for our coefficient of static friction. Right? So we need to end up somehow with force of friction divided by a normal force. Okay? Keep in mind that we know FWY here is equal to this side of our little parallelogram that we can create, and we know that that's opposite of that 30-degree angle. So we know FW is the hypotenuse because here's the right angle. So the sine of 30 is equal to the opposite, which would be FWX over our FW. Okay, and since I know FW is equal to mg, I'm going to substitute that in there. Okay. I can rearrange this to solve for FWX so that it's equal to mg sine of 30. Okay. Now I'm going to do the exact same thing for FWY. Notice FWY is adjacent to that 30-degree angle, and I'm again going to use FW as the hypotenuse, so that tells me I need to use cosine for my trig function. So cosine of 30 is equal to FWY divided by FW, but again I'm going to substitute in mg. So that when I rearrange this, I get FWY is equal to mg cosine 30. Okay. Now, again, because I know that FWX is equal to my force of friction, right, and my normal force is equal to my FWY, I'm going to take these two expressions, mg sine 30 and mg cosine 30, and I'm going to substitute those in to my mu s equation. Okay. So the coefficient of static friction is equal to mg sine of 30 divided by mg cosine of 30. Okay. Now we can simplify this a little bit. The masses cancel out. We can also cancel out our g's. So we take the sine of 30 divided by the cosine of 30, and when you plug that into your calculator, you should get 0.58. So our coefficient of static friction is 0.58. Okay, so in this example, we're going to find the acceleration of the block if mu k is 0.3. So again, because there's acceleration, we know that F net cannot be equal to 0. So what that tells me is that my FWX, right, is going to be bigger than my force of friction, because this block is actually going to slide down the incline. So we know two things here about F net. Okay, other than that, it's not 0. We know that F net is equal to MA, and we also know that F net is equal to my FWX minus the force of friction. Since I wasn't given an actual mass again, I'm just going to substitute in my equation mg for Fw. And since I know the angle of the incline is at 30 degrees, I also know that this angle is 30 degrees as well. So again, what that allows us to do is write two equations for Fwx, which we know is opposite of that 30-degree angle, and also for Fwy, which is adjacent to that 30-degree angle. So for Fwx, we know that that's going to be equal to mg sine of 30. Okay. And for Fwy, we know that's going to be equal to mg cosine of 30. Now I got those two equations just like I did in the previous problem, so if you need to see that again, go back and watch that part of the podcast again where it will show you how I rearrange the equation to get Fwx and Fwy. Okay. Now what I'm going to do is, since I know my F net is equal to these two things, right, I'm going to set those equal to each other. So mass times acceleration is equal to Fwx minus the force of friction. Okay, and since I'm solving for acceleration, I know I need to get that by itself, so I'm going to divide each of these by the mass. Okay. Now again, I don't know mass. It's not given to me. So I'm going to see if I can substitute some things in to get these to cancel out. So I know for Fwx, I can substitute in my mg sine of 30. Now I need something to substitute in for my force of friction. So we know that the force of friction, right, if we use one of our new equations, is equal to mu k, because this thing is moving and we know our value of mu k is 0.3. So it's equal to mu k times our normal force. Now again, because this is sitting on the incline, we know that our normal force is equal to our Fwy. Okay, so since I know that, I can take this portion, mg cosine 30, and substitute it in here. So the force of friction is equal to mu k times mg cosine of 30. Now I have something that I can substitute into my other equation over here on the right side of the screen. So mu k times mg cosine of 30, and again that's all being divided by m. Now because we have m in each part of this expression, I can simplify this by getting rid of the m's, and that's great because I again don't know what my value for m is. Now we know all of these values. We can plug this into the calculator. So we have our value of g, which we know is 10 meters per second squared, multiplied by the sine of 30, minus mu k, which was given to us as 0.3, times g, 10 meters per second squared, times the cosine of 30. Okay. And when you plug and chug all of this into your calculator, you should end up getting 2.4 meters per second squared. Okay. Now, if typing all of this into your calculator scares you a little bit, do each part of that expression on its own and then subtract the values. So 10 times the sine of 30 should give you 5. 0.3 times 10 times the cosine of 30 should give you 2.6. So then when you subtract them, you end up with your overall answer of an acceleration of 2.4 meters per second squared. Okay, in this problem we're solving for mu k when our acceleration is 2 meters per second squared. So again, because I know the block is accelerating, I know that F net is not equal to 0. And what that tells me, again, is two things. F net is equal to mass times acceleration, and also F net is going to be equal to the force of weight that's going down the ramp, so Fwx minus the opposing force of friction. Okay. Again, I'm not given the mass, so I'm going to look to substitute some things in so that I can cancel mass out and actually solve this problem. So I know I've got my ramp at a 30-degree incline, and we again know that that's going to be equal and opposite to this angle here. So we'll label that our 30-degree angle. We know that the force of weight is equal to mg, which is going to allow us again to write those equations for Fwx, which is equal to this side of the triangle, which is opposite of that 30-degree angle. So we know we'll end up with Fwx is equal to mg times the sine of 30. And I can do a similar thing for Fwy. Again, I know it's adjacent to that 30-degree angle. So Fwy is equal to mg times cosine of 30, just like in the last couple problems. Now, I also know that that's going in the opposite direction of Fn, and those two things have to be equal to each other, so I can also set this equal to my normal force. So I'm asked to solve for mu k, and so I know mu k is going to be equal to the force of friction divided by my normal force. Okay. Now I know I can take this part that I've just rearranged over here, mg cosine of 30, and substitute that in for the bottom portion of this equation for my normal force. So mg cosine of 30. And again, I don't know mass, so I'm trying to substitute things in, which is going to allow me to cancel out mass and solve for the problem. So if I go back up towards the top of the screen, I know I have F net, which is equal to Fwx minus the force of friction. And if I rearrange that to solve for the force of friction, that's going to be equal to my Fwx minus F net, which I can substitute in ma for that. I can also substitute in mg sine of 30 for Fwx, which is going to give me mg sine of 30 minus ma. So I'm going to take this whole thing now and plug this into my equation down here. So mg sine of 30 minus ma. Now again, notice I have mass in each part of this expression in my equation, so I can cancel out mass. Notice I can't cancel out g for gravity because it's not in the second part of the top equation. Okay, and so I have to leave that in there. But at this point, I know my value of g, I know my acceleration is 2, so I can plug numbers in and solve for this. So mu k is equal to g, so 10 meters per second squared, times the sine of 30, minus an acceleration of 2 meters per second squared, which is given to us, divided by the quantity 10 times cosine of 30. Okay. When you plug all of this into your calculator, get 0.35 for your coefficient of friction after you round. Now, if you're not getting that, probably what's happening is you're not using parentheses on the bottom, so just remember that you have to use that second set of parentheses, otherwise your calculator is going to divide by 10 and then multiply everything by the cosine of 30. Okay, in this problem we know that there's a 30 Newton force that is applied up the ramp. Okay? But that doesn't necessarily guarantee that this block is going to move up. We have to look at what its component is for FWX, and if that is greater than the applied force of 30, it's going to slide down the ramp. However, if the applied force of 30 newtons is greater than FWX, it will move up the ramp. So let's figure out, first of all, which way this block is going to move. Okay? To do that, I'm going to make my free body diagram. I know that my gravity is going to cause Fw, which acts straight down, to be equal to the mass times g. Now we know that the mass of this block is 3 kilograms, so 3 times 10 is 30 newtons. Okay. I know I'm going to have a normal force that acts perpendicular to that contact surface. I know I'm going to have an x component of weight, Fwx, and I also know that I'm going to have a y component of weight. Okay, so Fwy. My ramp is at a 30-degree incline, so I know that that angle is going to be equal to this angle right here. Okay. And because I know my mass is 3 kilograms, I can actually come up with a number now for Fwx where I couldn't in the last couple problems. So again, we can write our equation for Fwx because we know that that is opposite of this 30-degree angle. And we know now know our hypotenuse, Fw, is 30 newtons. We can say 30, right, which is mg, times the sine of 30, okay, which is going to give us an Fw of 15 newtons. Sorry, an Fwx of 15 newtons. I can do the same thing for my Fwy component, which is adjacent to that 30-degree angle. So for this one, I know I'm going to use the cosine of 30. So mg, or 30 newtons times the cosine of 30. And when you plug that into your calculator, that's going to give you an Fwy of 26 newtons. Okay. Now, if Fwx is equal to 15 newtons and the applied force, which is being applied up the ramp, is 30 newtons, that tells me that this block is going to move up the ramp, okay, because Fa is bigger than my Fwx. Okay. Now we just need to figure out with what acceleration. Okay. So the only other force that I can draw in now is my force of friction, which we know always acts opposite of motion. So since we've determined that it's moving up the ramp, I know my force of friction is also going to be acting down the ramp in the same direction as Fwx. Okay, I can actually solve for my force of friction with one of my new equations. Mu k is equal to normal force. Mu k is given to us as 0.3. And I've solved for my normal force because, again, we know that Fwy is going in the opposite direction as Fn, so we know that that has to be equal to 26 also. So 0.3 times 26 newtons is equal to a force of friction that is 7.8 newtons. Okay, we're getting closer. So we know that there is acceleration. That's what I'm being asked to solve for. So again, that tells me that F net is not equal to 0. So I can take two equations that I've been writing. F net is equal to ma, and F net is equal to the greater of the forces, which in this case is Fa, minus the forces that are going in the opposite direction. And remember, I have two of them. I have Fwx plus the force of friction. Okay, so I'm going to add those two things together. Now I can substitute in and say that ma is equal to this whole other equation for F net. So the applied force minus the quantity of Fwx plus the force of friction. Okay. To solve for A, I know I can divide each of these sides by m to get acceleration by itself. And now I know all of these numbers, so it's just a matter of plug and chug. So I have 30 newtons minus the quantity Fwx, which we solved to be 15 newtons, plus my force of friction, which we solved to be 7.8 newtons. And I'm going to divide that by the mass of the block, which is 3 kilograms. So when you plug and chug all of this into your calculator, you should end up getting 2.4 in units for acceleration. Remember, are meters per second squared. Now, in case you forget how you end up with that when you have newtons and kilograms, remember that 1 newton is equal to a kilogram times a meter per second squared. And so if I would plug this in on the top of my expression, the kilograms on the top and the bottom would cancel out, and it leaves us with meters per second squared, which we know is a good unit for acceleration.